So I realized when I was recording the last QOD video that I was flying so fast on the back end through all of the empirical gas laws that I really should go back and try again. And so this video picks up about halfway through the video of the last video, and I'm trying to slow it down and go into a little bit more detail. So let's just really briefly again talk about the gas constant R. And so as you'll recall, the ideal gas equation is PV is equal to nRT, where this is pressure, volume, number of moles, temperature, and the thing that relates them all together is R, which is called the ideal gas constant. Given to you here with a lot of different units, and so I just really want to simplify things for you. The two numerical values of the gas constant that I keep memorized and that I know are this one first, 0.08206 atmosphere liters per mole Kelvin. Sometimes it's just 0.0821 is actually the way I do it, but 0.08206 atmosphere liters per mole Kelvin. This is the value of R that you're going to use when you're solving any kind of gas law problem. And then the other one is 8.314 joules per mole Kelvin. And that's because the ideal gas constant actually doesn't have to do just with gases. The gas constant is actually what you get when you multiply what's called the Boltzmann constant by Avogadro's number. And so this comes up in thermodynamics problems a lot. And so later in the year, you're going to need to remember 8.314 joules per mole Kelvin. If you can remember these two, 0.08206 atmosphere liters per mole Kelvin or 8.314 joules per mole Kelvin, then you're fine. Calories per mole Kelvin, we're never going to mess around with. Pascal cubic meters, well, that's just the same as this because a Pascal cubic meter is equal to a joule. If you were doing an ideal gas law problem in which you were working in torr instead of atmospheres, you could use this value for R, but instead of having to remember this value for R, I just always, when faced with a problem like that, will convert torr into atmospheres so that I can use this value of R. So really, you can get by using these two values for R. Okay, let's talk about the empirical gas laws in a little more detail. And I've actually gone and created some new pictures rather than using the ones from the textbook. I kind of grabbed some pictures of my own. These are actually a couple photographs I took of myself. So here is a closed syringe at 60 milliliters, and that's at atmospheric pressure. So I just open it to 60 milliliters and then put a cap on. So the pressure inside is 60 milliliters. I mean, so the volume inside is 60 milliliters. The pressure inside is 1 atmosphere. If I compress that to half of its volume, 30 milliliters, then the pressure will go up. The pressure will double because volume and pressure are inversely proportional. And you can see that my poor little fingers here are sort of turning white-knuckled because I am trying to press this thing in and hold it at 30 milliliters. And this is now at 2 atmospheres inside instead of 1, which is a considerable amount of pressure to have to push against the thumb for any long period of time. So that's a sort of physical example of Boyle's law. If we graph volume versus pressure, you can say, let's just say this is 60 mils at 1 atmosphere. If I cut that in half to 30 mils, now the pressure goes up to 2 atmospheres. If I went down to 0.33, a third of what I did, or 20 milliliters, then that would be at 3 atmospheres, etc. That's what an inverse proportion plot looks like. You can get a straight line plot. Instead of plotting volume against pressure, you plot volume against reciprocal pressure. Now you've got a direct proportion instead of an inverse proportion, and you'll get a straight line. Now, let's just go back over this again. How does Boyle's law relate to the ideal gas law? Well, Boyle's law, in the case of Boyle's law, you're looking at the relationship between pressure and volume if the number of moles and the temperature are kept constant. So if the number of moles is a constant and the temperature is a constant and R is always a constant, then for a fixed sample of gas at constant temperature, these three things just become a single constant. We just say PV is equal to K. and therefore we can set we can set pressure and volume under condition 1 equal to pressure and volume under condition 2 because they both equal the same constant. And so we can say P1 V1 equals P2 V2. Now, what would be a typical problem that you would get in which you're employing this Boyle's law formula here? Well, here's one from a test bank. A sample of gas, and that is 5 moles of gas at 1 atmosphere, is expanded at constant temperature from 10 liters to 15 liters. The final pressure is what? Well, there's a little bit of a red herring in this problem, and that is the moles, because it is, as long as the number of moles stays constant, we don't care what it is, because that's not part of this equation. And so I'm going to look at the problem. I'm going to say, what am I being given and what am I being asked for? I'm being given initial pressure and initial volume and final volume, and being asked for final pressure. And so I'm simply going to take that formula and solve it for P2, which ends up being P1 V1 divided by V2. Substitute in the values they gave me. P1 is 1 atmosphere. V1 is 10 liters. V2 is equal to 15 liters. And I get the answer of 0.67 atmospheres. Does that make sense? Remember, these things are inversely proportional. So as volume goes up, pressure goes down. Volume went up from 10 to 15 liters. Pressure went down from 1 to 0.67 atmospheres. So there's a Boyle's law problem. Let's take a look at Charles's law. And I went and tried to get a nicer looking picture out on the interweb besides what's in your textbook. Here is a balloon at room temperature, and here's a balloon after some enterprising person has been pouring liquid nitrogen on it. Liquid nitrogen has a temperature of like minus 150 degrees Celsius or something. So it's pretty cold, and you can see that the balloon is very quickly shrinking. And so what Charles's law says that if I've got a fixed amount of gas at constant pressure, and this is at constant pressure because it's going to have the same pressure inside as outside, the atmospheric pressure. Fixed amount of gas at constant pressure, the volume is directly proportional to its absolute temperature, or its temperature in Kelvin. And so if I maintain a constant external pressure, a constant amount of gas, if I pour liquid nitrogen on it, the volume is going to decrease. And so if I plot, that's a direct proportion. So anytime the product of two variables is a constant, that's an inverse proportion. Anytime the quotient of two variables is a constant, that's a direct proportion. So if you plot volume versus temperature, you will get, with experimental data, you will get a straight line. I want to just stop here for a second and point something out to you, which is eventually, if you decrease the temperature of a gas enough, it will turn into a liquid. But if you just plot data like this before it liquefies, you can actually extrapolate down to what would be the temperature at which the volume was equal to 0. And this is how scientists knew what the value of absolute 0 was long before it was actually possible to achieve it experimentally. Because when you plot a straight line like this and then say, okay, if V over T is equal to a constant, or if V1 over T1 is equal to V2 over T2, eventually, if the temperature got down to 0, then the volume should get down to 0 theoretically. And so you can extrapolate, and that's how you determine that absolute 0 is minus 273 degrees Celsius. So let's try applying this to a problem. First of all, let's just go back and think about how this falls out of the ideal gas equation. PV is equal to nRT. Now I'm looking at the relationship between volume and temperature if I hold pressure and the number of moles constant. So if I've got a fixed sample of gas at constant pressure, I am going to now rearrange this so I've got volume and temperature on the same side of the equation. So I divide both sides by T, I divide both sides by P, I get V over T is equal to NR over P. If I am holding the amount of gas constant and I'm holding the pressure constant, and R is always a constant, I'm now multiplying two constants and dividing by another constant, which just gives me a fourth constant, which we'll just call K. So therefore, at fixed pressure and number of moles, V over T is always going to be equal to some constant. So no matter what set of conditions I do in terms of changing the volume or changing the temperature, as long as I don't change the pressure or the number of moles, I can set those two conditions equal to each other. And so that V1 over T1 is equal to V2 over T2. Okay, how would we get a problem like that? Well, V1 over T1 is equal to V2 over T2. Here's a problem. If a sample of a gas at a given pressure occupies 5 liters at 25 degrees Celsius, what volume will the same sample occupy at 100 degrees Celsius, given that it's the same pressure? So pressure is constant, the amount of gas is constant. This is a slightly modified version of the same problem that I gave you in class that it took everybody a while to get the right answer to because people were forgetting to convert Celsius degrees to Kelvins. But I start with this equation. I ask myself, what am I being given and what am I being asked for? I'm being given initial volume, initial temperature, final temperature, being asked for final volume, or V2. And so I'm going to solve the equation for V2. V2 is equal to V1 T2 over T1. Now I plug in the values. V1 is equal to 5 liters. T2 is equal to 100 degrees Celsius plus 273, 373 kelvins. T1 is 25 degrees Celsius plus 273, which is 298 kelvin. When I work this out, I get 6.3 liters. So there's a Charles's law problem. Now, how about Avogadro's law? This was the cleverest photograph I could find on the web. But if 3 moles of a particular gas occupies 30 liters, then 2 moles would occupy what? It would occupy 20 liters, and 4.5 moles would occupy 45 liters. This is a little problem for you to work out, but I've done it for you. Okay, Avogadro's law says that the volume of a gas at constant temperature and pressure, so I'm holding temperature and pressure constant, is going to be directly proportional to the number of moles of the gas. And this just makes total sense, right? The more air I put in the balloon, the bigger the balloon gets. Volume is directly proportional to the number of moles. V over N is equal to a constant. That's a direct proportion. Anytime two variables, the quotient of two variables is equal to a constant, that's a direct proportion. If the number of moles goes up, the volume goes up. If the number of moles goes down, the volume goes down. Okay, so let's just see how this falls out of the ideal gas equation. Since PV is equal to nRT, I'm now looking at the relationship between volume and the number of moles. So to get them both on the same side, I'm going to divide both sides by moles. I'm going to divide both sides by pressure. So for a gas at constant temperature and pressure, volume over the number of moles is equal to R times the temperature divided by pressure. If temperature and pressure are constant, and R is always a constant, I've got all 3 terms on this side are constants. Therefore, I can just replace them with a K. Volume divided by the number of moles is equal to a constant. Therefore, as long as I hold temperature and pressure constant, this will hold, that if I increase the number of moles, I increase the volume. If I decrease the number of moles, I decrease the volume. So what would a problem look like? Well, here comes a problem. Here's our equation. If 50.75 grams of a gas occupies 10 liters at standard temperature and pressure, in other words, I'm holding temperature and pressure constant, 129.3 grams of the same gas will occupy how many liters at standard temperature and pressure? I am holding temperature and pressure constant. So this relationship holds. Now you'll notice that it doesn't tell me what the gas is. It only tells me how many grams of each I have. So how can I figure out how many moles of each I have? Well, I don't have to, because as long as it's the same gas, the ratio of the mass of the 2 samples is also going to be equal to the ratio of the moles of the 2 samples. In other words, no matter what the molar mass is, 50.75 over 129.3 is going to be the ratio of the moles. And so in this case, I can simply, because grams of substance A divided by grams of substance A is equal to moles of substance A divided by moles of substance A. I can simply, I've rearranged, I've solved this equation now for V2, which is what it's asking me for, which is equal to V1 times N2 over N1. V1 is equal to 10 liters. And the initial mass is 129.3 grams. The final mass is 50.75 grams. It's going to occupy 25.5 liters. Does that make sense? We apply the smell test to our result. Well, I am taking the amount of gas and I'm increasing it by like 2.5 fold, right? Going from about 50 grams to about 100, little over 125 grams is increasing the amount of gas by about 2.5 fold. I increase the volume from 10 to 25.5, which is a little more than 2.5 fold. That makes sense. All right, I mentioned standard temperature and pressure on the previous problem. It said STP. What does that mean? Well, there's a defined standard temperature for gas law problems. There's a defined standard pressure for gas law problems. The standard temperature is 273 kelvins, which is 0 degrees Celsius. And I've just put a little warning in here because later in the year, when we start talking about thermodynamics and various properties, most listed thermodynamic properties of things are listed at 25 degrees Celsius, which is 298 Kelvin. You are going to have to make this distinction in your mind over the course of the year. That in most cases, the sort of standard temperature is 298 kelvins or 25 degrees Celsius. But for employing the gas laws, standard temperature is 273 kelvins, which is 0 degrees Celsius. And standard pressure is 1 atmosphere. And just remember, 1 atmosphere is defined as exactly 760 torr. And so I've just put 1 with a million, with several zeros after it, just to indicate that it really has infinite number. When we define standard pressure as 1 atmosphere, we're really saying 1 atmosphere with an infinite number of zeros after. And so this actually allows us to calculate something called the standard molar volume, which is a number that you will see often, along with Avogadro's number. This is a number that you will see often sort of associated with the concept of chemistry. The standard molar volume is what is the volume of a mole of any gas at STP? Well, by rearranging the ideal gas equation, volume is equal to nRT over P. We're saying that N is equal to 1 mole, R 0.08206, temperature is standard temperature, which is 273 Kelvin. Pressure is standard pressure, which is 1 atmosphere. That is 22.4 liters. So a mole of any gas at standard temperature and pressure is going to occupy 22.4 liters. All right, well, let's go on to the last bit of stuff that I wanted to talk about here, which is now we can apply all this to stoichiometry. So here's our old friend Roadmap 2 from Chapter 3. In Chapter 4, we realized we could mash up Roadmap 2 with Roadmap 3, and we had new ways of getting to moles, which is we can get to moles not only by dividing the grams by the molar mass, we can get to moles by multiplying molarity times volume. And then we can get from moles to molarity by dividing by volume, just like we can get from moles to grams by multiplying by molar mass. And so we had some new ways to sort of hijack Roadmap 2. Well, now we've got another new way to hijack Roadmap 2, which is we can get to moles of either substance A or B simply by solving the ideal gas equation for moles, which is N is equal to PV over RT. So we've got more ways now of getting at moles. And so let's do a problem in which we're actually going to go from grams of substance A to moles of substance B this way, and then determine a volume. So here's the question. 10 grams of sodium bicarbonate reacts with an excess of hydrochloric acid. In other words, sodium bicarbonate is going to be the limiting reactant. What volume of carbon dioxide is produced at 25 degrees Celsius and 1 atmosphere? Well, in order to solve this, you have to remember from chapter 4 that this is what's called a gas-forming acid-base reaction. A sodium bicarbonate is going to react with 1 equivalent of hydrochloric acid to give water, that's the acid-base part, plus sodium chloride, that's the salt part, plus carbonic acid, but carbonic acid, so it's going to give sodium chloride plus carbonic acid. Carbonic acid decomposes into water plus carbon dioxide. But we've got our balanced equation here. So we're starting with 10 grams of sodium bicarbonate. We have to, so let's just remind ourselves what we're doing here. We're going from grams of substance A to moles of substance A to moles of substance B to PV equals nRT. Okay. 10 grams, I'm going to convert that to moles by dividing by the molar mass. I'm now going to convert moles of sodium bicarbonate to moles of carbon dioxide from the coefficients in the balanced equation. That gives me 0.119 moles of carbon dioxide. Now I can use the ideal gas equation to convert that into a volume. Volume is equal to nRT over P, which is my moles, 0.119, times R, times the temperature, 25 degrees Celsius, which is 298 Kelvin, divided by the pressure, which is 1 atmosphere, and I get 2.91 liters. Okay, I've used up enough of your time. There will be a QOD coming up on these topics, and so thanks for watching.